Hello, my name is Justin Farnin. This is Steven over here, and we're from J&S Insurance. And today we're going to be going through our earthquake analysis. So, what is an earthquake? An earthquake is a natural seismic phenomenon characterized by moving and shaking of the ground. The range in size from mild tremors to violent destruction of large geographies, and they can be modeled as waves with amplitudes traveling across the Earth's surface. Now, major earthquakes have never been predicted by a scientific model because of their unpredictable nature and potential for catastrophic damage. Seismologists and insurance actuaries use statistical analysis to assess the probability of major earthquake events occurring in a given location over a specified period of time. Now, why do we really care about this? Well, as we look to move into the Southern California area, we want to be able to forecast the energy level for specific areas in LA. We want to be able to predict different energy levels dispersed from the earthquake. This way, when we're recommending insurance products to these areas, we know what kind of coverage should be considered based on the previous year's data and the forecasted energy levels. That way, the customers have the right coverage given the amount of energy from those earthquakes. The data that we used for this was from USGS, a branch of the Federal Department of Interior. We have 222,000 plus observations ranging from January 1970 all the way up to September 22, all in the LA area. The main features include the daytime, longitude and latitude, depth, and magnitude.
Yeah, and just let's take a minute to talk about earthquake size. What are the measures of earthquake size? The most common one is magnitude. For example, the Richter scale is an example of earthquake magnitude. These are logarithmic scales. And so a magnitude 5 versus a magnitude 6, well, magnitude 6 is actually 10 times more, 10 times bigger than a magnitude 5 earthquake is. And there's formulas here that you could see on the screen that will actually calculate the magnitude of an earthquake. There's also energy. So earthquakes are ultimately a release of energy across the Earth's surface. And so you can think of these as being waves traveling across the Earth's surface. And there's also a formula relating the magnitude to its release of energy. There's a few different formulas out there. We have one here that's pretty common and recommended by the USGS. And so each unit increase, so magnitude 5 to magnitude 6, well, the magnitude 6 is actually a 32-fold increase in energy release. And then there's earthquake intensity. This is a more subjective measure. It's things like, oh, did I feel the floor shake, or did my dishes break? Did any furniture move? It's a little closer to an assessment of economic damage. There are standardized ways of measuring earthquake intensity, but by and large, it's a very subjective measure. We can move on to the next. And so we have actually chosen to look at earthquake energy specifically rather than earthquake magnitude. Part of the reason is what's actually happening is that there are tectonic plates across the Earth's surface. They're being driven by thermal energy inside of the Earth. So you can think of earthquakes as being the mechanical energy release of the thermal energy phenomenon happening inside the Earth. Also, earthquakes are distributed over a region. So there's an epicenter, and then energy is dispersed from there. And so we can take distance-weighted energy contributions at different locations across the LA region. And we can actually add energy together just like a linear function, as opposed to magnitude, which is kind of wrapped up in this logarithmic equation. And then finally, the last reason we want to use energy is because large earthquakes are rare and orders of magnitude more energetic than smaller ones. So if we add up all the energy contributions of a bunch of magnitude 1 earthquakes, it's not gonna ever seem as though it's a magnitude 7 earthquake or anything like that. As you can see in this chart here, where there was a very large energy release, it looks like around 2006 or so. And all the months before it and after it, you don't even come close. So we can move on to the next one. So ultimately, we want to create a time series predictive model. So our approach is that first we assume an inverse relationship between the wave energy and distance. You can see here that some of that is based on data. There's also ideas in physics, amplitudes of water waves thrown in a pond decreasing over distance. And then using that idea, we can calculate the energy contribution of the earthquake at each lattice point. So you can see here, We have a 21 by 21 grid of lattice points that we've created across the LA region. And if an earthquake happens in San Clemente, let's say, we can calculate how much energy was impacted at Irvine, how much energy was impacted at Long Beach, how much energy was impacted at Santa Clarita, right? And so we can then sum all of those contributions that occur in a given month and then compare month over month to try and create some kind of time series predictive model.
Perfect. So given that Stephen transformed the original data set into that grid point data set, we now have 441 features. And the next part of the EDA is for the decomposition plots. And I didn't want to make 441 plots. So I did a random sample out of those grid points and did 10 of them. And they're all pretty much the same, so to speak, a little bit different here and there, but this is what one of them looked like. I'm just going to run through basically what this is. So we have the original, the trend, and the seasonality, as well as the residuals plots. For the trend and the original, we can see some spikes here and there, and then as they decline, it kind of flattens out. The seasonality, this basically indicates to us if earthquakes happen in a particular part of the year. So maybe some happen more in the winter, some happen more in the summer. This is not the case, they just happen whenever. And then for the residuals, this just shows any leftover variability that isn't shown in the trend or the seasonality plot. And these plots are also good indicators to determine if your data is stationary or not. So stationary data, that would look more, or think of a stock price. If the stock price is going up and up and up and up, you know, we will see that as non-stationary data. But so we want this line to be a little bit more flat, kind of like we see here, to be stationary to feed into the model. So in order for us to kind of get a better idea of that, we did the augmented Dickey-Fuller test and the KPSS test. Now, if the p-value for the Dickey-Fuller test is below 0.05, then it is stationary. And if it's above 0.05, then it's non-stationary. And for the KPPS test, if it is below 0.05, then it is considered non-stationary. And if it's above 0.05, then it's considered stationary. So these are kind of contradicting to us right now because we have one saying it's stationary and one saying it's non-stationary. And given the different grid points that we have here, it all depends. Some of them are going to have higher p-values for the ADF and some are going to have lower. So given this, we decided to kind of look at one more plot, which is right here. And this is just the rolling mean and the rolling standard deviation. And again, it's kind of looking like the trend in the original plot that we saw before. So we did a little bit of experimenting. We did one model with stationary data, and then we did another model with non-stationary data just to kind of see how they performed. And then one other thing that is very important for time series is also looking at the partial autocorrelation. So the partial autocorrelation will help you indicate how far back you want to look at to make those future predictions. And I'm going to go into the notebook to show you what that looks like. So right here, so again, I looked at 10 columns, and the way that you would interpret this is for these lines right here that are outside of this blue box, that are significantly outside, those are the ones that you're going to want to count. You can count the minor ones too, like this one and this one right here, but the major ones are the ones that are going to, give you the better predictive power, I would say. You can count these ones, but it's just all playing around with the numbers. So we have 1, 2, 3, 4, 5, 6 around. Maybe you can get more out of those. I would say maybe 6, but it all depends on how many you want to do. And when I went through and counted all of these different ones, you can see that it's all different shapes and sizes the farther we go down. Some of them are more intense, like this one as well. So for the modeling part, I just did 6 for looking back in the past. So it's going to be looking back 6 months to predict the future values. Now you can adjust that. And also if your data is in days, then you're going to do it to 6 days. Or if it's in years, it'd be 6 years. Okay. Alrighty. So the first model that I built was just a regular linear regression model. This data was basically split 80-20, 80% training, 20% testing. The lagged columns that are in here, as you see right here, that's basically just making the data stationary. So it's basically taking the percent change or the difference in Python terms, and then sticking those columns as the X's. And then for the Y values, we didn't do any of that. So those are going to be our testing or our predicting values. So those aren't going to be our target values. So those aren't going to be lagged. And basically when we did this, as we can see the results on the next slide, it looks perfect. Looks like we have a perfect model right here. Everything in the blue back here is the training, and then this orange over the blue is our testing. However, this is a result of data leakage. Now, data leakage is when the model inadvertently gets access to the testing, the target variable, which makes predictions appear more accurate than they truly are. So I think this RMSE score or the error score is about 0. Obviously, that's not something that can go off, but I wanted to show that this is interesting because the linear regression model probably is a good model to use, but just the way that it was executed in this case isn't the best. So this is something that we need to be aware of as going forward in the analysis to help make sure that this doesn't continue. Alrighty, and then the next model that we built a few different models using the Scalecast package. So we only used it on 10 columns. The reason for that was because every time I ran with more than 10 columns, it would just crash. So basically just got the first 10 columns, split it again into 80-20, used the auto-aggressive term, which is going to be looking back 6 months, set that to 6. And then from there, I set a generate future values of 5 years. And then we ran 4 different models. So that's where you ran an LSTM neural network, a multiple linear regression, a lasso regression, and an XGBoost. Perfect. And as we can see here, we have all these models placed on here. The LSTM model down here, which I thought was going to be actually really good because it's good for complicated data, actually did pretty poorly, even when adjusting with it. So this is the best that I could get it. The multiple linear regression lasso model, which is basically the red right here, and the multiple linear regression is just under that. They did all right. In the beginning, it's picking up everything, but it wasn't able to pick up this variability right here, this huge change. Going forward is pretty constant. So it's not a bad model to use, but the XGBoost, as we can see here, is able to pick up these larger spikes. Even though some spikes are more exaggerated than others, it was able to pick up these higher readings, which is something that we were looking into and something that we did want because these higher readings kind of happen sporadically. And if we just have like a multiple linear regression or a lasso regression that's great at picking up these values, it might not be great at picking up this one right here. So that's why we decided to kind of dig more into the XGBoost model a little bit.
Yeah, like Justin said, the XGBoost, not only did it do the best back tested against past data, it also most aligned with our intuition for how we might think of earthquakes occurring. And so a standard metric like RMSE or mean absolute error or anything like that, what you're doing is for every month subtracting the predicted value from the actual value. Well, that's just no good for us because we don't think we can predict earthquakes on a month-by-month basis. But over, let's say, a 5-year basis, we should be able to say, hey, here you can see a model in real life. 8 magnitude 2 earthquakes occurred, and our XGBoost model predicted something like 7 magnitude 2 earthquakes occurring over that 10-year period. So that's something a little bit closer to how we would want to gauge our models. Although sometimes they go very, very wrong, as you can see over here in grid point number 7. We actually predicted way more earthquakes of magnitude 2 than actually happened. So we just need a little bit more time to just understand what's actually going on under the hood to assess some of the variability here. And Justin, if you could jump to the notebook here, and this is all contained in our GitHub. So you can see a page right here, just kind of describing what we just talked about. If you just keep scrolling down, you see we just have keep going, just never stop scrolling. So we just have these functions for our these 10 different grid points where we are assessing the 10 years of back tested predictions, aligning them with actual data and just seeing how they perform. Some of them do really well, like this one we just passed. Some of them, yeah, see, 7 actual earthquakes and 9 predicted earthquakes. If we keep going though, we'll run into some trouble. And we just need a little bit more time and more resources to understand exactly what's going on here. Yep. See, there's just ugliness. And then also when it comes to future predictions, so if you just keep scrolling even more, keep going, keep going. So these are, future predictions. Now, obviously, we don't have any way of assessing the accuracy of these because, predictions are hard, especially about the future. But this is, again, the XGBoost seems to be creating something a little more aligned with our intuitions for how we think earthquakes should occur in a stochastic and random manner. And then Justin, if you'll skip to the next notebook there. Just for due diligence, we want to do a classical statistics analysis where we try to find the distribution of earthquakes, and then we find, the mean, standard deviation, maybe like a z-score or something like that. So if you just scroll down a little bit more, we found that there's actually a nice histogram here, a nice distribution of earthquake, the logarithm of earthquake energy. Keep going down, and this actually fits a log normal curve. I can't tell you how happy I was when we finally found this, there actually is a function that fits this. We can actually do statistical analysis. So scroll down a little bit more. You can just see the same chart again. And so what we decided to do, if you scroll down just a little bit more, past the graphs. Sorry, I put a lot of graphs in here. So right here, we're trying to determine, so you can see there were 143,000 magnitude 1 events in our data set, 34,000 magnitude 2 events, and so on. Does our log normal distribution predict something like that? So we're using z-scores to find the probability here. I'm just using standard log normal analysis where you take the logarithm and it should create a normal distribution. Keep scrolling down. And we actually have some predictions here. It's the very next thing, I believe. The very next series of printouts. So you could see that our model predicted 2,800 events, and there were actually 2,600 events happening per year. We predicted 677 magnitude 2 events per year, and there were actually 640. Not bad at all. But when we get to the magnitude 5, magnitude 6 events, we start deviating a little bit away. So the classical statistics analysis, works pretty well. And this is what our insurance actuaries would probably use to classically determine the risk assessment of an earthquake happening in any given area. But we want to do better. So that's why we're trying to do beyond classical statistics and actually try to create predictive models for all these different lattice points around the LA region. So if we jump back to the slides, so our next steps really do involve, our next steps really do involve working with an actuarial team to determine the economic cost and, hiring geologists to make sure, hey, all those assumptions that we made, are those realistic assumptions that we're making? And Justin can speak a little bit more to the cloud technologies here that we would need.
Yeah, so when we were running this analysis in Google Colab, again, we weren't able to run it on all 441 grid points. We're only able to run it on 10. So after we did that, it kind of crashed. So if we were looking at something like AWS, Azure, GCP, something to kind of run this into so we can run it on all grid points, that would be great, as well as building some type of ETL or ELT pipeline. So it's constantly pulling data and it's constantly being updated and feeding the model new data as it gets it in. That way we don't have to kind of sit here and run it manually. And then we can just have this as an application and have it just run all the time. That way our insurance agents can kind of see this. And when they're making all these recommendations, they're getting live data, they're getting live feeds to make sure that all the recommendations for different insurance products are accurate. We also want to do more of a deep dive into the Scalcast package, which I was showing before, or which I ran my model in before for the LSTM and the XGBoost model. It's a very newer model, or newer package, I should say. It's only been around for a year or two, so there are some bugs in it that need to be worked out, as well as trying to make a multivariate time series model work rather than a univariate. So every time it was running through each column, it was univariate, but I want to be able to run all of them at once to make it multivariate. So the package, it's like I said, it's very new. So doing a lot more deep dive into the package documentation to understand it fully. That way we can actually do it because it does run really well. It's great to set up for pipelines. So when we do all the ETL stuff, it'll be seamless. Perfect. So there's this
and this
one.
is a Yeah, this is just our necessary slide. I feel like we were pretty collaborative. We did different parts, but I feel like we were pretty collaborative in checking in with each other throughout our progress throughout. You feel it differently, Justin?
No, it was we did different things, but we also did a good amount of different things, and we met once or twice a week with any questions or problems that we had, and we figured it out together. We worked really well together. It was great.
I agree. And that's it. That's our technical presentation.
Yep,
Let's jump into the
technical.
executive summary, put a new hat on.
Perfect. Alrighty, so earthquake energy executive summary. So how can our insurance company break into the new era and provide outstanding service to new customers if they've never had to sell insurance to states that have earthquakes like California? So basically we were able to forecast potential earthquakes over the past 5 years to make, or are we able to forecast potential earthquakes? Sorry, are we able to forecast earthquakes over the next 5 years to assist in making the best recommendations for our client? Partially, yes. I'm going to say yes. We'll get into that a little bit more. I was
Yeah.
very confident when we did. I was happy. So again, we built a series of different predictive models that show promising results. Again, the XG Boost one, we'll get into that a little bit more, but that was really nice to see, along with the statistical analysis. That was really good to see as well. So again, the objective that we had was just gathering data from the USGS in Los Angeles that was basically from 1970 to 2023 for all 12 months and just predict 5 years out. What is the benefit of this? Well, we can help make sure that our new customers in the LA area have the right coverage. So if anything does happen, that they're covered and their homes are safe and that they feel valued and that they're covered. Earthquakes can ruin livelihoods. And we don't want people to be homeless. We want to make sure that everybody has the correct insurance in place, no matter where they live in the LA area, because every parts of LA gets hit with different energy levels of the earthquake. So we make sure that everybody's has the right coverage in place. And then I'm sure if you want to take it from here, Stephen, I keep going.
Yeah, determination of budgets for super catastrophe events. What's really interesting about this is that, as you can see in this distribution chart below, this is real data from 53 years of earthquakes that have actually occurred in or near the LA region. Earthquakes all absolutely do follow patterns. I think that's the most surprising finding, because we think of earthquakes as being these disasters that kind of come out of nowhere, but they really do follow a pattern. That means that there's something underlying it that we can use to our advantage, and try and assess the likelihood of earthquake damage happening in different parts of the LA region. And so if you move on to the next slide, ultimately, we built some models and we were able to forecast 5 years of future earthquakes for 10 of our lattice grid points that we created across the LA region. It's somewhat accurate in predicting past events. So the top chart that you see here, it predicted, I believe, 8 events where there were actually 7 events that occurred. Not bad. The problem is that we don't feel that this is quite ready for assigning pricing insurance premiums to any of these values yet. Our current system just can't handle it, but with enough tools, with a little bit more technology and research, and having more experts, we feel that this is actually a pretty promising area of research.
All right, so conclusion. So currently our model is not production ready for the accuracy and performability. However, we feel really great with where we are. The findings that we saw, the patterns that we found. We just again need more funding to get the model to where it needs to be and getting all the technology and experts that we need. So the benefits, so when this model is built, we'll be able to instill trust with the new clients if we're able to forecast the magnitude of the earthquake that they may experience between 1 to 5 years. Again, we're able to forecast 5 years out. We could probably go a little bit more, or a little bit less, depending on the model. And this also allows us to become more knowledgeable in the earthquake data space. So when we break into this new region, we know about the earthquakes, how it affects the people in those areas and what the damages are, but also the underlying numbers and how the energy can be dispersed and what areas might have experienced more energy or magnitude levels than others. And again, make sure that we're providing our customers with superb customer service.
Yep. Then we just have one more for next steps. Again, working with our actuarial team to actually assess the cost of earthquakes in the locations that our clients exist. Because if we can predict earthquakes, even to the day and to the hour, who cares if we don't actually know how much an earthquake event is going to cost in terms of economic damage. And then we also just want to hire just more people like geologists to make sure that our analysis is good. We just need more resources to help with the compute side of things and a deeper dive into some of our software packages. So we just need more. It's
More
a
time.
promising area.
Yes, exactly. All
I
right.
believe that's
Cool.
it.
And that's it.
Thank
So
you.
thank you and have a good night.